All right, so we are going to learn a new way to measure angles, which is called Radian Measure. And the reason why we like Radian Measure is because it's sort of like a more true, real measure of an angle. So let's write that down as part of our definition. And the reason for this is that the radian measure, as we measure this for an angle, is actually connected directly to the circumference of a circle. Who remembers, take your brain back to grade 9, who remembers the formula for circumference of a circle? Mathushini? It is 2 pi r. So if we think about circumference of a circle, so let's just say first directly related to circumference of a circle, which is, as Mathushini said, 2 pi r. So the 2 pi part of this is actually the radian measurement for one rotation around a full circle. It's like 360 in degrees. So this is one rotation around a circle. And of course that rotation, so the circumference is going to change if the radius is bigger or if the radius is smaller. So we take into consideration the rotation around the circle, and then for circumference calculation, we take into consideration how big the radius is. But the 2 pi part of that actually represents one rotation around a circle. And then let's talk about what is 1 radian. So 1 radian is actually the measurement that's needed to make the radius of the circle, as if we were to put a string on the radius of the circle and sort of wrap it around the curve of the circle to make those two things equal. So I'll show you a picture. So if this is my circle, that's a bad, really bad circle. It's a little bit better. So if this is my circle and I have the radius of that circle right here, I would need to rotate this from here a certain amount to make this red part right here, the radius, as if I had a string, to make it wrap around this part and to make those two things equal. Okay? So this is 1 radian in here to make these equal. And we abbreviate radians just with RAD. So it is the rotation needed to make the radius equal to the arc length. Okay, and this is the arc length right here. So obviously one is a curved measurement and one is a straight measurement. So the best way that I can explain this is if we put a string here and then we take that string and we wrap it around here, we want those two pieces to be the same with that length of string. That's the idea. Okay, and we'll talk about what that 1 radian measurement is and how that might look in degrees, because maybe that might help us think about what this actually is equal to. So degrees, we use degrees a lot. That's sort of the more modern unit of measurement that we use to measure angles. But radians actually make a lot more sense when we tie it to circumference of a circle and when we actually think about what 1 radian is actually equal to. Degrees is sort of more like an arbitrary measurement, right? Like who decided that 360 was around, like the measurement around a circle? Who decided what 1 degree was? Whereas 1 radian actually makes sense because we're trying to make the radius and the arc length equal in the circle. Okay, so I want to talk about some important values that we talked about last year in grade 11. You'll notice that a lot of our stuff that we talk about in this unit is a repeat of grade 11, but just in our new unit of measurement, which is radians, instead of degrees. So Our important degrees from last year, we started with these sort of important quadrants here, where we had 0 degrees. Where's my black here? There it is. We had 0 degrees, we had 90 degrees, we had 180, 270, and 360. Who remembers this from last year? Is this ringing a bell a little bit? We had all the different quadrants. Okay, and we said that the key relationship between degrees and radians, if 2 pi represents 1 rotation all the way around the circle, 2 pi must be equal to 360 degrees. And of course, if I have 0 degrees of rotation, then I also have 0 radians of rotation here as well. So this is 0 radians. And this is also 2 pi radians at this location, just like this is 0 and 360. Okay, so if our key relationship, I'm going to use maybe some of this area down here to help us as we go. So if our key relationship is that 2 pi is equal to 360, how could I find 180? What would 180 be in radians if I know that 2 pi is 360? Billy? Yeah, so I'll do, if 360, if I half that, I get 180. Then I will half it to get the radian value. So half of 2 pi is just pi. Okay, and I'll put that in over here for the 180 location here. All right, so we've got pi for 180. How about the 90 location now? If I know 180 is pi, what do we know about the connection between 180 and 90? Lexi? So what's 180 divided by 4, though? Mm-hmm. Or maybe I'll ask it this way. 180 divided by what equals 90? So, Lucas, this should be? Right, or in other words, we just say pi over 2, right? Half of pi. We usually wouldn't, because if I write a half, then I would just multiply the pi up on top anyway. So we'll just say pi over 2. Nicole? That's just to indicate that that unit of measurement is radians and not degrees anymore. Okay, so 90 is pi over 2. 90 is half of 180, so that makes sense, right? Okay, 270 is not down here, but if I want to create 270, it might be hard to do from 180, but 90 times what equals 270? Carol? So if 90 times 3 equals 270, what would 270 be in radians? Carol? 3 pi over 2, because 90 times 3 is 270. So if I do pi over 2 times 3, I just get 3 pi over 2. Perfect. So now we have all of our quadrants here. I could also use the relationship to find, remember we had our special triangles from last year, so we have some special angles that will give us exact values in these quadrants as well. So some of these exact values would be things like all these lines in here. Oh, I thought that was a highlighter. Hold on 1 second here. Let's do green. Okay, so I've got all these lines in here as well, which are all 30 degrees apart, including these, right? They're also on these inside quadrants here. So we're going to fill out all of these solid lines in here. And all of these sort of go up, and they go up by 30s. So this is 0, 30, 60, and then 90, and then 120. 150, 180, 210. I'm ignoring the dotted lines right now, okay? 240, another 30 degrees is 210, then 300, then 330, And of course, we go all the way back around to 360 here. So this is all counting up by 30 degrees. So let's talk about 60 and 30. I'm going to use 180 for this. What's the relationship between 180 and 60? What do I need to divide 180 by to get 60? Athena? 3. So this must be pi over 3, right? So 60 is pi over 3. How about 30? What's the relationship between 180 and 30? What do I need to divide 180 by? Carol? 6. So what's the radian value then? Lucas? Pi over 6. Perfect. Okay, we'll leave 45 and 1 for a couple minutes. Okay, so this is pi over 6, we said. That's equivalent to 30. This one is pi over 3. And I can use relationships like this, right? Like if I think about maybe the relationship between 30 and 120, then I can do multiples of these things and stuff like that. But I actually really like to fill this out by just counting. All I really need to do is count by pi over 6s. So if I know that one slice is pi over 6, then I know the next one will be 2 slices of pi over 6, right? Which is 2 pi over 6. What does 2 pi over 6 reduce to? So pi over 3, right? Which we already have figured out in that. Sorry, I'm just trying to, I don't know why this won't let me slide up here. Sorry, guys. We have to delete this out. Why? Why are you doing this to me? Okay, let's just add an eraser on here. There we go. Keep that. Okay, so 2 pi over 6 really just reduces to pi over 3. The next slice, if I count up again, now I have 3 slices of pi over 6, right? So this would be like 3 pi over 6. What does that reduce to? The 3 and the 6 reduce, and I get pi over 2, right? Okay, next slice will be 4 slices of pi over 6. So 4 pi over 6. What does this reduce to? Lucas? 2 pi over 3. Next slice will be 5 pi's over 6. So 5 pi over 6, that one doesn't need to be reduced, right? That one's already reduced. Next slice, I'm just counting, right? So 6 pi over 6, this reduces to pi. That one's already filled out. We don't need that one again. So these ones I'm just going to erase. We don't need them. So 6 pi over 6, keep that in your mind. Next slice, what will the next one be? If pi was 6 pi over 6, the next one will be 7 pi over 6. So let's just fill them in quickly here. That's 7 pi over 6. This will be 8 pi over 6. This one would be 9 pi over 6, 10 pi over 6, 11 pi over 6. And then, of course, the full rotation here will be 12 pi over 6, but we already have that one filled out. Then you can just go back and you can reduce all the ones that need to be reduced. So I'm seeing that 8 pi over 6 can be reduced. What can we reduce that one to? Athena? 4 pi over 3. So let's reduce that to 4 pi over 3. Okay, 9 pi over 6, that one's already filled out. It reduces to 3 pi over 2, so I don't need that one. How about 10 pi over 6? Can we reduce that? Lucas?
5 pi over 3.
5 pi over 3, so reduce that to 5 pi over 3. Can we reduce 11 pi over 6? No. And then full rotation, 12 pi over 6 already reduces. It's already reduced there. It's 2 pi. Does that make sense? We're just counting up by pi over 6s and then reducing all the fractions there. Okay, so that's, I like to do that when I fill out the chart, personally. Sorry, I just deleted this green one here. Okay. Let's talk about the dotted lines inside here. The dotted lines are all the 45s. So here and here, including these, right? These ones are also 45 apart, so we're also using the 0, 90, 180, 270. So these are our last lines that we need to fill in here. Okay, so let's talk about the relationship then between 180 and 45. How can I go from 180 to 45? What's the divisor? What would I need to divide? Billy? Divide by 4, so that means that 45 must be equal to pi over 4. That's what we're going to count by, starting from the first dotted line. So it will be 0, 1 pi over 4 radians. Okay, so now I'm counting here. Maybe I'll do this in another color here. Now I'm counting this. Just can't get back to my pens. Okay, so one slice here, pi over 4. Next slice is here. This is 2 pi over 4, which reduces to pi over 2. That's already labeled. We don't need that, but just keep that in your mind. This will be the next slice of 45 degrees, which will be 3 pi over 4. This one will be 4 pi over 4. Next one, 5 pi over 4. So you're just counting up by pi over 4s this time. 6 pi over 4. 7 pi over 4. And 8 pi over 4, which reduces to 2 pi. So then you're just going to go through and you're going to reduce these if they're reducible. So this one I don't need. That's already labeled there. It's already reduced. 3 pi over 4, can I reduce this? No, so we'll just leave it. I'm just going to do it in black here. 3 pi over 4. 4 pi over 4, of course, reduces to pi. So that's good because that's at that location already. 5 pi over 4, can I reduce that? No, so let's leave that one. 6 pi over 4 should reduce to this, which it does, so that's good. So we can just erase that one. We don't need it. Can we reduce 7 pi over 4? I don't think so, so that one can stay. 7 pi over 4. And then, of course, the final one is 8 pi over 4. I didn't write it, but we know that that reduces to 2 pi. And I'm just going to move this one over a little bit here. Okay, does that sort of make sense how we can label this whole thing? I can also, again, use relationships, right? Like if I know 30 times 4 is 120, then I know pi over 6 times 4 will give me this same value here, and then I reduce it, right? So you can always just use relationships like that as well. If you know like how to fill in the first few, then you should be able to get all of them with relationships of 30s and relationships of 45s as well. So either way you want to do it, whatever you feel comfortable with. I think counting just makes sense, and then you just reduce all the fractions around. That's easy to do, as long as you know that 30 is pi over 6 and 45 is pi over 4, which you can always figure out with this idea that we did down here. Okay, so let's talk about one degree. What is 1 degree equal to in radians? So what's the relationship? How do I go from 180 to 1? Esther? Divide by 180. So 1 degree should be equal to pi over 180 radians. And this is actually a key relationship here. We're going to use this to switch between degrees and radians and degrees. So this is another way that you can actually fill out this entire, oh, we forgot to fill these in. So this is 45, 135, 225, and 315. Sorry about that. So that's actually another way that you can fill in the whole thing. If I just know how to switch between degrees and radians, if I know how to fill this in degrees, I should be able to use the relationship that 1 degree is equal to pi over 180 radians, and I can switch all of them into radians. So lots of different ways that you can fill out this or know all of these radian degree angles here. Okay, so let's work on switching between degrees and radians and degrees. So anytime I have degrees, I'm going to multiply by pi over 180 radians to switch into radians. And then if I'm trying to do the reverse of that, if I have radians and I want to switch into degrees, I'll multiply by the reciprocal, so 180 over pi. So if I have 65 here, I'm going to multiply by the relationship that we talked about here. Multiply by pi over 180. And you'll have some things that cancel. Sorry, I'm just trying to get my pen set up here. Okay. To leave an exact format, we're going to see what's the greatest thing that we can divide into both 65 and 180, and we're going to reduce. So usually in radian form, we want to reduce as much as possible without expressing as a decimal. So let's grab our calculators here, and what is the greatest thing that I can divide into both 65 and 180? If you want to reduce a couple times, you can always reduce a couple times. Not 18. So I think we can divide 5 into both of these. That's what you were going for.
38.
So if I divide 5 into both of these, then I will have 13 left here and 36. Yeah. So this will be 13 pi over 36 radians. Okay, and then of course the opposite here, if I have 5 pi over 7, I will multiply by the inverse of what I just did, so not 360, 180 over pi. And usually what you'll see happen is if the initial radian value has a pi in it, the pi's will cancel. And then I'm just going to multiply 5 times 180 and divide by 7. And then I should have my degree value. You could leave this in exact format. Like if I multiply on top, I get 900, and if I divide that by 7, I'm going to get a decimal. So one way that we could express this would be just to approximate it. So approximately 128.57, or if you want, you can also express it as 900 over 7 degrees if you want to express it exactly. Usually I'll just say round to the nearest hundredth, like 2 decimal places for degree values. Okay, so we're going to do a little bit of practice here. I'm going to give you guys a couple minutes to do number 4 and 5 here. For these ones, actually, all of these can be expressed in exact form, so you should not need to round to the nearest hundredth. So for all of these, we're going to express in exact radian form, fully simplified. And then once you finish that, if we haven't taken this part up, you can move on to number 5 and see if you can express these all in degrees. Okay, so I'm going to give you guys a couple minutes to do that. Okay, so there's our first one. Second one, this is what you should have gotten, so you can double check your answers. Okay, this is an interesting relationship. We talked about what is 1 radian at the beginning of this lesson. And 1 radian was the rotation needed to make the radius equal to the arc length. And that turns out to be about 57.3 degrees. So that could be something that would be helpful to know as well, is that the rotation that's actually needed to make the radius equal to that arc length is about 57.3 degrees. Any questions on these two? Oscar, can you just pull your mask up there? Thanks. Okay, so the last two things for today, I'm going to introduce a new formula to you, which works for any kind of like rotation type questions. It's the arc length formula. And it says that theta, the angle in radians, is equal to the arc length subtended by the angle. So essentially just the arc length that's created by rotating a certain theta degree or theta radians. And r will be the radius of the circle. So an example of how we can use this would be a wrench. So a wrench with a length of 23 centimeters rotates around 0.36 radians. Find the arc length traveled by the wrench. So let's suppose we have our wrench here. And we know that our wrench is 23 centimeters. And that wrench gets rotated 63 radians. And I want to know what is the curved length, so the arc length, which will be represented by A. That's what we want to find. Okay, and then the radius is 23. So let's plug in what we know into our formula. We know theta is 0.63 radians. Theta must be entered in radian value for this formula to work. Arc length A, we don't know. And radius, we do know it's 23 centimeters. So I can get A alone very easily just by multiplying that 23 up on both sides. These will cancel. And what do we get as our arc length? Oliver? 14.49. And because the radius was in centimeters, this will also be centimeters as well. All right, our last part for today, I just want to talk about our special triangles. So do you guys remember our 45, 45, 90 triangle and our 30, 60, 90 triangle from last year? Those good old special triangles. We're going to just do them, but do them in radians this time. So our 45, 45, 90 is our isosceles triangle. I'll still use the right angle box to indicate a 90-degree angle, or in other words, a pi over 2 radian angle. 45 is pi over 4, so we'll call this the pi over 4, pi over 4, pi over 2 triangle. Does anyone remember what the 45, 45, 90 triangle side ratios were from last year? Taking it back. Athena?
Was it
1, 1, not 2, very close. Billy? Root 2, yes. And if you can't remember, you can always plug in 1 and 1 into Pythagorean theorem and just solve for the hypotenuse. Okay, and our other one was the 30, 60, 90 triangle. So in our case now, that will be the pi over 6, pi over 3, pi over 2 triangle. And does anyone remember the side lengths of this one from last year? Lucas?
Was it like 1, 2, root 3?
It is a combination of 1, 2, root 3. So the rule is that the smallest side goes across from the smallest angle. And pi over 6 is the smallest angle here. That will be the side ratio of 1. The middle angle should go across from the middle side. And now I can't erase. So that will be across from pi over 3, which is root 3. And then the largest side should be across from the largest angle. So that will be the hypotenuse here. Okay, so we're going to fill in our chart. Let's start with the pi over 6 and pi over 3 triangles here. If I choose pi over 6 as my reference angle, this will be opposite, adjacent, and hypotenuse. And we're just going to plug these in for sine, cos, and tan. So remember, sine is opposite over hypotenuse, cos adjacent over hypotenuse, tan opposite over adjacent. So sine of pi over 6, I'm filling in this part of the chart here. Sine of pi over 6 opposite over hypotenuse should be 1 over 2. Cosine adjacent over hypotenuse should be root 3 over 2. And tan opposite over adjacent should be 1 over root 3. Okay, let's do the pi over 3 section. So if I choose pi over 3 as my reference angle, this now becomes opposite, and this becomes adjacent. This will stay as hypotenuse, right? That will be the same no matter what our reference angle is. Okay, so sine of pi over 3 opposite over hypotenuse, root 3 over 2. Cosine adjacent over hypotenuse, 1 over root 2, 1 over 2, not root 2. And tan opposite over adjacent, root 3 over 1. That will just reduce to root 3. Okay, let's fill in the pi over 4 one. We'll use our pi over 4 triangle. Doesn't matter which pi over 4 you choose, right? You'll get the same answers. So let's say we choose this one. This is opposite, adjacent, hypotenuse. And we're going to fill in sine, cos, tan. So opposite over hypotenuse, 1 over root 2. Adjacent over hypotenuse, 1 over root 2. And opposite over adjacent, 1 over 1, which we can just write as 1. Okay. Last year we talked about the unit circle and how we can find sine, cos, and tan of 0, 90, 180, 270, and 360. At least I know we did in my class. Not sure about Battering's class. But for now, we're going to use our calculator and practice with calculating some radian values on our calculators in sine, cos, and tan. The thing is that we need to actually switch the mode of our calculator so that our calculator knows we're inputting angles in radians rather than degrees. So what we need to do is we need to change the mode on our calculator, and I can help with that if people can't find it. So switch over to radian mode. Let's pause this for a second. Now that we're in radian mode, we're going to practice here. So we're going to do, let's start with 0 radians. We're going to take the sine of 0 radians, the cos of 0, and the tan of 0. And let's record what we get. So sine of 0 radians, what should that equal? Athena? You should get 0. I will also get the same thing if I plug in 2 pi, right? Because they're on the same location of the circle. So you can try 2 pi or you can try 0. You'll get the same answers for both. Okay, how about cos of 0 or 2 pi? Lexi? Should get 1, and tan of 0 or 2 pi. Billy? 0? Good. Okay, let's do pi over 2. Sine of pi over 2. Should get 1. Cos of pi over 2. Athena? 0. And tan of pi over 2. Matushini, what'd you get? Okay. That is because tan of pi over 2 is undefined. So I'm just going to make a little legend down here. U will be for undefined. And we will find out a little bit more about this later in this unit, so don't worry too much about it right now. But for now, it's just undefined at that value. Lucas?
For some reason, I got negative 0.5 cos. I got yeah. Like,
For cos of pi over 2?
yeah.
Did you do this?
No.
That's probably why. It probably did cos of pi and then divided it by 2, I'm guessing.
Oh, yeah.
Okay. Let's do cosine and tan of pi now. So sine of pi. 0. Cos of pi. -1. And tan of pi. 0. Okay, last one. 3 pi over 2. So sine, cos, and tan of all of those. -1 for sine, 0 for cos, and tan. Error undefined for through pi over 2. Okay, so we'll call it here. What we're going to do for homework is, if you are done studying for your logarithms test, you can of course work on this today. My suggestion would be work on your logarithm stuff today. I'm going to assign this whole worksheet. It's not very long. So just have this done before the next class. That's all, not the next class, like the class after our test. So that's all you need to have ready for Monday. You can just save it for practicing over the weekend or whatever, just as long as you have it done before Monday.